the first lesson I talked to you about section A, the experimental section. I said you read that, you spend a maximum of 1 hour on that part of the paper. You don't even look at section B at that point. You build up your confidence. I told you how to study for it as well. Just get your flashcards, do a bit of practice of leaving cert questions, and you'll be okay. Now we're moving into section B. I suppose section B could be called the theory section. It's regarded as more difficult than section A. So there's 280 marks here. That's 70% of the marks out of 400. How many questions do I have to do? I have to do 5 out of 8 questions. I mean, there is a good choice. Students say, can I leave out some electricity? Can I leave out some mechanics? Well, it is possible to leave out parts of the course and be lucky, but you can also be unlucky. Because one of the things they do is, occasionally they will mix some heat in with some nuclear physics or some mechanics in with some light and sound. The Doppler effect, which is light and sound, appeared as part of an electricity question one year. So they can mix them around. So obviously the more of the course you get done, the better. But you may be able to leave certain things out that I'll talk about as I go through this. So I've got to do 5 out of 8 questions. 280 divided by 5, that's 56 marks per question. The first question in section B, question 5. Everybody should do question 5. I've finished section A after a maximum of 1 hour. I turn to question 5. I still don't read the paper. I want you to do question 5. Because question 5 is a mixture. It's a mixture of all parts of the course. And they're 10 short questions. 10 short questions from part A down to part J. This is what I suggest. You finish section A, you're feeling nice and happy because all you've done is done some diagrams, some graphs. Now I go into question 5. I open up my exam paper like that, my exam script. I write down question 5. I write down part A, skip 3 or 4 lines, write down part B, skip 3 or 4 lines, and go all the way down to part J. And I actually don't feel like I'm doing a question when I do question 5. It's 10 short questions, very simple stuff like definitions, little formulae, a little bit of real life physics. They can't ask you anything too difficult. So there's very, very short little questions. And I don't even say how long you should spend on it. I say to you, you should do this throughout the rest of the exam, throughout the next 2 hours. It's a mixture of everything. So you might see a question, oh yeah, I know that. So you fill that in. Yeah, I know that, I'll fill that in. You might immediately fill in 4 or 5 parts. Then you move on to your next question. And when you're finished your next question, go back to question 5. You might now fill in 2 or 3 more parts. Then go on to question 8 or question 9 or question 10. Finish that and keep going back throughout the exam and keep on filling this in. It's a mixture of the entire course. So you'll get thinking about nuclear physics, you'll get thinking about photoelectric emission, you'll get thinking about all parts of the course. So I'm not even saying how long you should spend on that. I'm just saying that for the next 2 hours, you should continually fill in those 10 parts. Even though there's 10 parts, you've only got to do 8 out of 10 parts. 8 into 56, that means every one of these questions is 7 marks. Can't do them all. Like, it's the only part of the paper where you can actually get 2 wrong and still get 100% of the marks, because they will pick the best 8 out of 10. So everybody should do question 5, definitely. Let's move on now. Next question, question 6. Every single year It's been a full question on mechanics. And it may be quite a difficult question on mechanics, involving all kinds of satellites, astronauts going to the moon, all kinds of planetary motion going on. So it can be quite difficult. If you love your maths, and if you do applied maths, obviously you want to do the mechanics. The mechanics is a definite. But if you did want to leave a question out, you could leave out that full question on mechanics. Now that doesn't mean I'm telling you to leave out mechanics. You're still going to be doing the mechanics experiments for section A. You're still going to do all your basic mechanics, your definitions and so on, because mechanics can appear around the course. But I'm saying that tough question on mechanics that can involve satellites, gravitational and circular motion, you may decide not to do it. But that's your decision. Question 7 and question 8. Actually, I think those 3 questions, 6, 7 and 8, they may be the toughest questions on the paper. Question 7 could be a full question on light and sound. Could be a full question on electricity. And occasionally a full question on heat. I don't know. They all move around. Can't say for certain. They're tough questions. 6, 7 and 8. All these questions, of course, are 56 marks. Question 9 is usually the question on modern physics, which I did in the Christmas revision course. Modern physics comes in 2 major parts. Part 1 is all about the electron. You're talking about things like photoelectric emission, X-rays, fermionic emission, the cathode ray tube. And part 2 is nuclear physics. Now the notes for those are quite short. I mean, as I said to you when I was talking about the content earlier, the 3 biggest sections are mechanics, light and sound and electricity. Modern physics is quite short to them. And I always tell my students, you should do the modern physics question. There's a fantastic return on it. And it's not very waffly either. You're using your calculator. There's a lot of intelligent stuff in there. So question 9, I would always tell my students to do. The modern physics occasionally changes. It might be question 8, but it's in there somewhere. Question 10 is your option question. Again, I tell students to do that because the option that we choose is particle physics. And particle physics is very, very, very short. It's so short that they sometimes ask some modern physics from the nucleus, like the nuclear reactor, in the particle physics. There's 2 options. Part A, that's the particle physics. I think 90% of the country do that. I do it as well. But you know, you can't do the particle physics unless you've done the nuclear physics. So they go hand in hand. So I have to be able to do the modern physics in order to do the particle physics. But it's very, very short. It's usually question 10 part A, but sometimes they get a bit sneaky with it. They throw that into question 12, but they did that last year, so I suspect this year it'll be a full 10 part A question. Part B is the other option, which is the applied electricity option. That's actually a lot longer. I wouldn't bother doing both options. I mean, I'd say very few students, unless you're completely in control and love your physics and want to do absolutely everything, you would do 2 options, but mainly you would just do the 1 option. So that's a nice question to do. Question 11. Question 11 is called the STS question. STS stands for Science, Technology and Society. What it actually is real life physics. So in other words, you're studying maybe the Doppler effect, and they want you to know the applications of it. The applications might be to find the speed of stars, or to act as speed traps, to stop cars speeding. So we're talking about real life physics. Now, it can be a nice question to do. First of all, it could be about any part of the course, but they start off by giving you a nice paragraph. And read the paragraph very carefully, because I would say 2 or 3 answers could be contained in that paragraph. And then they will ask you 8 parts altogether. You've got to do all 8 parts. That's 8 by 7, which again is 56 marks. You know, they're short questions, so again, they can't ask you anything too difficult. So if you know your definitions and you've done learning very, very well, and you read your paragraph, it can be a nice question to do. So question 11, yes, I would recommend that. Question 12 is another question that I would recommend. Question 12 is a nice question because they're half questions. You know, if I do a question 7, they could ask me a difficult question on diffraction, which we did earlier, or a difficult circuit. But in question 12, because they're only half questions, they can't ask you anything too difficult. There are 4 parts to it. You've got to do 2 out of 4 parts. Any 2 out of 4 parts. Part A, B, C, and D. Part A, usually a short question on mechanics. So when I said to you, okay, it's safe enough to leave out that tough question on mechanics, sometimes it's not that tough by the way, but to leave it out, you should still be able to do basic mechanics, and you should be able to do something like 12 part A. 12 part D is usually a question on modern physics. And you know the way it goes. If the question 9 on modern physics, if they ask the electron there, they'll ask the nucleus there, and vice versa. Which kind of brings me to an important point as to why I want you to do modern physics. Modern physics, which I include the particle physics in my modern physics notes, they're all together, and even though they're all together, they're still only half the size of the mechanics, the light and sound, and the electricity. But if you look at it, you have the potential to get 2.5 full questions from modern physics. Question 9, question 10 part A, and then 12 part D. So if you think about it, that's now 2.5 questions, and you've got to do 5 altogether. So half of section B is now done through the modern physics. So I always recommend students concentrate on the modern physics. And what are the other questions about? Well, they could be on anything, heat, light, or whatever. So, a good strategy would be, in my opinion, you know, for the least amount of work that I do, I would do question 5, but I have to learn all my definitions and so on. Everybody should do question 5. I would concentrate on my modern physics, which includes the particle physics. That'll give me 2.5. And then I've got to think about it. That's 1 question, 2 questions, 3 questions, 3.5 questions. Well, if I do that half, I've got to do another half. So I've got to pick 1 more of these. That's 4 questions. And then go and find 1 more question, like the STS question, question 11. That's a strategy. So, that's the course. How long should I spend on each question? Well, we talked about a maximum of 1 hour on the experimental part. I'm not really putting a time on question 5. I kind of do that as I go along. So I suppose I'm talking about, for the rest of the questions, I'm talking about 20 to 25 minutes. I'm doing question 5 as I go along, so 20 to 25 minutes on the next 4 questions. Look, I find more or less that students, when they do the physics paper, they're not under huge time constraints. They get it done quite comfortably. They have a little bit of time left over, so they can go back and recheck on their paper, maybe even do an extra question. So that's my paper. Now, I told you how you prepare for section A, getting your flashcards and doing the essential information. The essential stuff you want for the experiments are diagram, suitable graph or formula, and experimental details. So I told you how to study for that. How do I study for section B? Everything I've talked about, by the way, is all detailed very clearly on page 2 of your guide. Let me talk about how you get ready for section B. I'll go to this board here. I talk about the mundane. And I talk about the intelligent. Like, I love teaching the intelligent, I love doing the intelligent. Intelligent is what we were doing earlier. We were doing diffraction problems, we were using our formulae, we were using our calculator. That's the thinking intelligent part. Now, if you just concentrate on the intelligent part, it doesn't matter how brilliant you are, unfortunately you won't get a H1. Because a certain amount of paper involves the mundane, the boring, where you've got to do your definitions, you've got to do your demo experiments, you've got to do all of these things. So we can't get away from that. The intelligent is just you practicing all of the examples in our notes. But the mundane, let me try and break down the boring, mundane for you. So whether I like it or not, these are the things that I have to do in order to get my H1 in physics. In the mundane, I've got to do definitions. Now, the definitions are throughout the notes. I've given you a full list of definitions. So if we go to the light and sound, for example, section, page 12, every definition is given there. The nice thing about definitions is, a number of definitions, you can actually use a formula. So for example, if they said to me, define electric field intensity. Well, you could write that down in words as a definition, or you could say, actually, there's a formula for that in the table book. So E, the electric field intensity, is F divided by Q. If you actually do the definition, then write down what everything stands for. Write down that E stands for electric field strength or intensity. F stands for force. Q stands for quantity of charge. And also put in their units. For example, force is measured in newtons. Now look, all of that is freely available in your table book. Because the next thing you have to do in the mundane are your formulae. Well, since you got the table book about 10 years ago, since students got the table book about 10 years ago, they don't have to learn their formulae anymore. That's the way it should be. Nobody should have to learn formulae off by heart. So basically, your formulae are there. In your notes, I've written down what page number the formulae are on. You should colour in the formulae that you need. I've also, you can see here, in your summary, I've given you all the formulae. I've written down what page number they're on. And I put some little diagram beside them, just to give them a little bit of context. So if you're talking about the wave equation, there's a little wave there, just so you can think a little bit about it, instead of just seeing formulae there without any context. So every formula you need is written down there, and their page number. Occasionally, we don't have the formula in our table book. So if that's the case, well, you just have to learn it. I mean, there is one particularly well-known formula that's not there. It's the formula for current. I is equal to Q divided by T. That's not in your table book, so you have to learn that. But that's pointed out in your summary. So look, nothing to do with formulae. Definitions, I'd say about half of them can be written down as a formula. But you won't get full marks just by writing the formula down. Write down what everything stands for and their units. But look, you don't have to learn that off either, because there's an alphabetical listing at the back of your table book telling you whatever letter stands for and what their units are. That's the way it should be. You don't have to cog anymore. You don't have to write down sneak little notes into the exam. It's now freely available to you. So that mundane isn't too bad. What else do I have to do? This I call the heavy learning. You have to learn these demo experiments, demonstration experiments. These are different to the experiments, the mandatory experiments that we do in section A, those 20 experiments that we talked about earlier. These are little demo experiments. Look, I've given you a full list of them. How do you demonstrate reflection? How do you demonstrate refraction? How do you demonstrate total internal reflection? How do you demonstrate Young's experiment to show that light is a wave? They're all there. This is the heavy learning. Now, when you do them in the exam, what you really need to know is a nice diagram followed by a short paragraph. You don't have to go on and on about them. So a short paragraph and a nice diagram. How many demo experiments are there throughout the notes? I don't know, I haven't counted them up, but I'd say between 50 and 60. So you have to learn them. I call that the heavy learning. They'll ask you, how would you demonstrate such and such? They'll probably ask 2, 3, 4 of them in every exam, so they are important. So what else do I need to do for the mundane? Well, we've got to do proofs. We talked about a proof earlier on. The proof for n lambda is equal to d sine theta. So that's the only proof for light and sound there. I have it in those types of boxes, double line boxes. So you have to do your proofs. How many proofs are there altogether? Let me go back in my guide. Page 5. There's a list of mechanics proofs called derivations. There's only 1 in light and sound, 3 in electricity, and say 3 in mechanics. So you're talking about 7 proofs altogether. So in terms of learning, there's not a huge amount to do there, but you should do them. You know, they will ask every year, they'll probably ask 1 proof somewhere along the course. What else do I need to do? The last part of the mundane is called, I mentioned it earlier, STS. We talked about the STS question, didn't we? Which was over here. Question 11 was the STS question. So we're talking about real life applications. Now these are throughout the course. I've listed them. So this STS about waves, about the Doppler effect, speed traps, uses of mirrors. They're throughout the notes. But look, the nice thing about them is I don't have to learn them like I have to learn the demo experiments. I just have to read them. Just read them and familiarize yourself with them. Because most times when they ask a question about them, they're just asking maybe for a 1 or 2 word answer. They might ask you, what's an application of the Doppler effect? Something very, very simple. So all you should do there is just read, 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 familiarize yourself. So don't regard this as heavy learning. That's just some light reading and you will familiarize yourself with the real life applications. So that's the mundane. Definitions, okay, half of them are formulae, which is good. Formulae, well, most of them are in the table, which is great. Demo experiments, that's the heavy learning. Proofs, yeah, there aren't too many of them, even though they're a bit of a pain. And STS, just read. So the mundane isn't that bad. The intelligent, well, that's about you doing question after question after question using those formulae. So we've already done a certain amount of that in the previous lessons. Now, anything else on that? Yeah, is there any other learning you have to do beyond that? Well, of course, there's a few other things. So, in each particular topic in your revision guide, I've put in other topics. So, for example, you need to know the ray diagrams for mirrors, the ray diagrams for lenses. They're all there. You need to know something about the spectrometer. I've got some frequently asked questions that they always keep on asking done here as well. So there's other bits and pieces, and then we're back to our Section A experiments. So there's a summary there of every single part of the course. Now, Section B is regarded as harder than Section A, but look, it's just a question of being organised. I always say to students, you don't have to be a brilliant student to get a H1 in maths, but you have to be in physics. You don't have to be brilliant at maths to get a H1 in physics. But you need to be very well organised. And I suppose the one thing I can do for you is to organise you. So that little guide I've given you contains a summary of every part of the course, and it's a way of organising you. Okay, so I'll leave it there. Thanks very much. Let's get stuck into some content. Overall, this is the entire content of the Leaving Cert. I know you have a book and these chapters might be all over the place, but essentially at the end of the day, your content is light and sound. That's all about the waves, resonance, diffraction, mirrors, electricity. You've got circuits, capacitors, Coulomb's law, electromagnetism, mechanics. You're talking about free fall, you're talking about momentum, you're talking about gravitational circular motion. Those three there, I'd say they're the big ones. They're the longest sections on the course. And you have a full set of notes. Full set of notes and full set of solutions for all of those. Some very small section heat. And then modern physics. I did this over the Christmas revision course. We've got modern physics, and associated with modern physics we have the option. Now there are two options. The option I always do is the particle physics, but you can't do the particle physics unless you do the modern physics. I think about 90% of the country actually do the particle physics. It's interesting. It's all about your quarks, your muons, your taus, and so on. Anyway, I will not be doing those sections in this particular course. These are the big three that I'll be talking about in this particular course. Now, let's get stuck in. Let's start with light and sound. Now, the opening chapters in light and sound, chapter 1, chapter 2, chapter 3, they're all very basic stuff. There's stuff to do with drawing array diagrams in mirrors, drawing array diagrams in lenses. You work your way through it. Basically, what you want to do is go through the notes, fill in all the gaps. Because basically, the way we work is this. There's a chapter 4 on light and sound. Inside these notes, I've chosen nice examples. I've tried to choose one of every type of example. You work your way through that. You try to do it. If you can't do it, then you can look at the solutions. The solutions are in there. So you gradually work your way through the notes, filling in all the gaps. In the notes, you have everything that you need. You have all the different parts of the course, but I'll be talking about Section B later on anyway. When I'm finished a particular chapter, at the end of every chapter, I have a load of numerical problems. Different kinds of numerical problems. Many of them haven't appeared on the Leaving Cert yet. You work your way through those. You have the answers to all those questions. And once again, if you get stuck, they're all done in the solutions. And then finally, at the very back, you've got every single Leaving Cert question that they could possibly ask you. So look, everything you need is there available to you. You just need to work through it. So there's the course. So let's start. I'm going to start with the parts that they ask most regularly on the higher level Leaving Cert. I'm going to go to chapter 4, which is called the wave nature of light. Chapter 4 is on page 44 in your notes. Yeah, before I do that, just going to go over to this board here and just talk a little bit about waves. So you all know what a wave is. You've been studying it since junior cert. If you wish to revise it, then you look at chapter 1, the notes that I gave you, and that will give you a full explanation of everything to do with waves. But I just want to refer here to a really important equation. And this is one of the most important equations that you're going to have on your Leaving Cert physics paper. It's called the wave equation. You know, they're going to ask that 3 or 4 times in the exam in June. Not because I've seen the paper, but because I've asked it 3 or 4 times in every exam that they've ever asked on physics. There is a wave, like a water wave or a light wave or whatever kind of wave you want. You have something called the frequency. The frequency F, that stands for the number of waves generated per second. If you're talking about a water wave and you move your hand up and down in the water, the frequency of you moving your hand up and down will generate the waves. So if you move your hand up 10 times per second, you generate 10 waves per second. The frequency is measured in hertz. Waves per second is also called hertz. The top of a wave is called a crest, and the bottom of a wave is called a trough. The distance from crest to crest is called the wavelength. And the letter we use for wavelength is a Greek letter called lambda. So lambda stands for the wavelength. We'll measure that in meters. And the last part of the wave equation is the speed of the wave. That wave will go at a certain speed to the right. Now I prefer to call the speed v, because it could be a sound wave, could be a light wave, could be a water wave. But the way it's written down in your table book is they use c for the speed of the wave. Now I tend to use c for the most famous speed of all, which is the speed of light, 3 by 10 to the power of 8 meters per second. But they're using c in general for speed. So it's the velocity or the speed of the wave. And speed, velocity, is measured in meters per second. That's your famous wave equation. You're going to use that, as I said, 3 or 4 times in June. Right, so look, if you're not sure about it, it's all there in chapter 1. You read it, you do the examples, you do all the numerical problems at the end, you've got all the solutions available to you. So you do what you need to do in order to get yourself ready for this part here, chapter 4, which is the part that they ask. So, first topic in chapter 4 is something called interference. I suppose we all have a sense of what interference is. You know, when the reception on your television goes a little bit, waves are merging together. Sometimes they merge together and you get a stronger signal. Sometimes they merge together and you get a worse signal. So, good interference, I suppose, I'm going to call constructive interference. In short, CI. Bad interference, when you tend to lose your signal, I'm going to call that destructive interference, or DI. Let me take a situation where I've got 2 waves. So, let me start with CI. So here's a wave. What kind of wave is it? I don't care. Could be a water wave, could be a light wave, could be a sound wave. Makes no difference. Here's another wave. Everything about those 2 waves is the same. Their starting points are the same. They start there and there. So I would say those 2 waves are in step. I suppose a better way of saying in step would be in phase. So they are in phase. Everything about those waves is exactly the same. They have the same height. The height of a wave, which you'll find out if you go through chapter 1, is called the amplitude. So they have the same height, the same amplitude. They have the same wavelength, distance from crest to crest, the same frequency. They're the same types of waves. There's no way a sound wave would interfere with a light wave. So everything about them is the same. And if everything is about them is the same, we say they've come from the same source. You know what a source is? A source is something that generates a wave, like a light bulb. That's the source of a light wave. Or a tuning fork, that's the source of a sound wave. So we would say that these waves have come from coherent sources. Everything about them is the same. That's quite an important definition actually that they like asking. That definition is on page 45 in your notes. So it says to me, coherent sources give rise to waves of the same frequency and amplitude which are emitted in phase or step. That's your definition of coherent sources. Now, if you have waves that came from coherent sources, they are able to interfere. They're able to merge together. These two waves here will merge together in a stronger way, in a good way. You see the top of that wave, the crest, and the top of that wave, the crest? But when they come together, you will get a much higher crest. So I'll end up getting a wave that's much higher, and I'll also get a much deeper trough. The low part of the wave is called the trough. So when these two waves come together in phase, you end up getting a much stronger signal. So if you're receiving two radio stations in two different ways, if the waves come together in a good way, you will get a nice strong signal. What about destructive interference? Well, destructive interference, the waves tend to cancel each other. So here's my first wave. And my second wave is going to be at a step. So let's say it starts a little bit earlier. It actually started back here. It actually started half a wavelength. You know what a full wave is, right there. That represents a full wave, doesn't it? That would be a wavelength. Well, right there, you've got half a wavelength. So I would say right here that these two waves are half a wavelength out of phase, out of step. Now what happens when they merge together or they meet? Well, look, you see the high point of that wave? That's the crest. That meets the low part of that wave, the trough. And as a result of that, you end up with no wave whatsoever. They cancel each out completely. So you have this situation where the wave has disappeared. So you get no signal. You might get a partial signal if they're not quite out of step, not quite half a wavelength out of step or phase. But we're just going to do the extreme situations of total DI or total CI. You could have partial DI, but we're not going to do that. Now, that's what we call the minimum condition for DI. But you know what you could have? You could have that wave that started 1.5 waves behind, or 2.5 waves, or 3.5 waves. So you could be half a wavelength out of phase. That's the minimum to cause DI. When we do mathematical problems, that's what they will be asking. But you know what? It could also be 1.5, which is 3 halves. Or it could be 2.5, that's 5 halves. And so on, and so on. Whereas over here, you know, when they're in phase, they're in step. But also, you could say this one could have started 1 full wave behind, which actually makes no difference, does it? So I could also say they're in phase, or they're 1 wavelength, or 2 wavelengths, or 3 wavelengths out of phase. It's important that you know. It's important that you know what the condition is for constructive and destructive interference. That's written down. What I've talked about there is written down at the end of page 44. That's important. Also, there's a load of definitions there. And these definitions are a bit of a pain. There's a lot of definitions that we can actually use a formula, so we don't have to learn it off. But in this particular case, there is no formula, so you have to learn your definition for interference, your definition for CI, and your definition for DI. They're all listed down there on page 44. And of course, over the page, you have your definition for coherent sources. Right, let me do a question on this, example 1. This is one very like this, was on the Leaving Cert a number of years ago. Example 1. So let me go through it. It says radio waves of frequency 30 kilohertz. You know when you hear radio waves, you might think to yourself, they're sound waves. Well, they're not sound waves. The sound comes out of the loudspeaker on your radio, but the waves that actually carry it to your radio are called radio waves. Radio waves are waves that travel at the speed of light. They're part of the electromagnetic spectrum. So, just going to write down my information. This particular problem. So the first thing they tell me is that the frequency F is 30 kilohertz. See that kilo? It's probably one you know pretty well. That's 1,000. But that in general is called a prefix. Now you've got lots of prefixes in physics, maths. Kilo, that's 1,000 or 10 to the power of 3. But there's lots of them that you won't know. For example, something like a nano is 10 to the power of minus 9. A mega, a centi, you know, a milli, a pico. You can't be expected to learn them off, but they won't tell you what they are. They'll expect you to go to the table book, and the place you find them in your table book is page 45. There's a list of them. So when you're doing this course with me, you have your notes in front of you. You have your calculator. You don't just sit there watching passively as I do this class, because I know this stuff inside out. You need to get it into your head. You need your calculator, you need your table book, you need to be an active learner if you're going to get the best value out of this class. So anyway, kilohertz, that's 10 to the power of 3. So you get rid of your prefixes. You turn them into their power of 10. Or 10 to the power of 3 is actually 10 by 10 by 10. That's 1,000. So you can turn that into 1,000 if you want. So I turn that into 30,000 hertz. So get rid of your prefixes. Page 45 is the page to go to. What else does it say? Radio waves of frequency 30 kilohertz are received at a location 1,500 kilometers from a transmitter. Here's my transmitter here. Here's me, the receiver. And we are a total distance of 1,500 kilometers apart. The distance between T and O is 1,500 kilometers. So what am I doing? I'm building up my picture. I'm writing down all of my information. It tells me the radio reception phase due to DI between the waves travelling parallel to the ground. So there's a transmitter, a radio station transmitting its radio waves, carrying whatever program is on the radio. And one way they go is they go along the ground like this. That's one way they go. Radio waves, they're not dangerous at all. They're very, very weak. That's why you're going to need aerials to pick them up and then to amplify them so you can actually hear what's going on. They have very, very long wavelengths. So they can actually leap over mountains. They can go around the curvature of the earth a little bit. So there's one way the receiver can receive the signal from the transmitter 1,500 kilometers away. But there's another way. There's a layer of ions high up in the atmosphere called the ionosphere. It's like a mirror in the sky for these radio waves. So the radio wave can also go up to that mirror in the sky, high, high up. I don't know how high up it is. It can bounce off that mirror just like it would do when you do your laws of reflection. You know what your laws of reflection are? The angle of incidence, I, is equal to the angle of reflection, or. Exactly the same thing applies here. They bounce off the ionosphere and they come to the receiver. So two ways my receiver can receive the radio signals: along the ground or by bouncing it off that mirror in the sky. Part A, they're asking me to find the wavelength of the radio waves. Lambda is equal to question mark. Now, you need to know that a radio wave is actually a light wave. It's a light wave you can't see, but it travels at the speed of light. So another very important part of your table book is pages 46 and 47. Those pages contain all your major constants. For example, the speed of light, c is there, and I'm going to write it down as 3 by 10 to the power of 8 meters per second. Look, they're given to tremendous accuracy. They might be given to 6 decimal places. There's no need for you to be that accurate to write down 2.45678 and thinking you're very, very accurate. Don't bother doing that. Just round them off to 1 or 2 decimal places. There's a part of the course, Modern Physics, where we actually use a few more decimal places for a different reason. But in general, just write down your constants to 1 or 2 decimal places. But you have to go and get them yourself. Those constants will not be written on the paper. So what am I going to use? I'm going to use my famous wave equation. My wave equation is c is equal to f lambda. They're asking me to find lambda. So lambda is equal to c divided by f. 3 by 10 to the power of 8 divided by 30,000. Now, as I said, as we're doing this course, have your calculator in front of you. Don't just be watching me doing it on the calculator. Be an active learner. So press my fraction button, 3 by 10 to the power of 8 divided by 30,000. And I get, on my calculator, 10,000 meters. Could write that down in scientific notation, 1 by 10 to the power of 4. They're the proper units. But you can see there 10,000 meters. You know what 10,000 meters is? I might change that to kilometers. And the only reason I'm thinking about changing it to kilometers is, you see that distance there is given in kilometers? Well, think about that. I'll write it down in kilometers for now. 1,000 meters is kilometers. That's 10 kilometers. So you can see the wavelength of a radio wave is enormous. 10K. That can leap over mountains. It can go around the curvature of the earth. They're also very, very weak. They have very little energy because they have this very, very long wavelength. They have a very low frequency. If you have a low frequency, you're low energy. Part B. It says, what is the minimum distance that the reflected wave should travel for DI to occur? Just back to this DI lesson here. You know, the minimum distance, I said they're half a wavelength out of phase. Obviously, this reflected wave has to go further, doesn't it, than that one along the ground. The question is, how much further did it go in part B? Well, it went half a wavelength further. That means they're half a wavelength out of phase. That means DI occurs. Notice they used the word minimum. So if they didn't use that word minimum, well, that reflected wave could have gone 1.5 wavelengths further, or 2.5. So it's important that they use the word minimum. Half a wavelength further. And what's a half a wavelength equal to? A wavelength is 10 kilometers. Half a wavelength is 5 kilometers. That's how much further it went. So what's the question they're asking? What is the minimum distance that the reflected wave should travel? Well, we're talking about the distance it travels. that 5k is the extra distance it travels. Well, that's 1500 kilometers from T to R along the ground. The reflected one went an extra 5 kilometers, and that means my answer for that distance would be 1500 plus 5, that's 1505 kilometers. Part C. The layer at which the waves are reflected is at a height h above the ground. Calculate the minimum height for di to occur at the receiver. Well, look, essentially I'm finished with the physics. I'm now just going to be doing some simple maths involving Pythagoras. I've got two right angle triangles there. I'm just going to concentrate on the one on the left to find h. The angle I is equal to the angle R. So basically that right angle triangle on the left is exactly the same as that. So this point here is the midpoint of TR. If that's 750 kilometers, this here is 750. So it's 1500 from T to R, that's 750. The total distance to go by bouncing it off the mirror in the sky, that's 1505. Divide that by 2. That means each side is 752.5 kilometers. So now I'm going to do a little bit of Pythagoras. If it's not very clear to you, you could draw it out. So for part C, I could draw out that particular triangle. There's the height h. The base of the triangle is 750 kilometers, and this is 752.5 kilometers. So now you're just going to apply Pythagoras to that. So square the two smaller sides, h squared plus 750 squared is equal to the hypotenuse squared, 752.5 squared. I'm going to solve that for h. H squared is, jump the 750 squared across where it becomes minus. Finally, that's h squared, isn't it? If I want h, I'm going to get the square root of all of that. So h is the square root of 752.5 squared minus 750 squared. So put that into your calculator. Square root of 752.5 squared minus 750 squared. And I get, let's round it off to one decimal place, I get 61.3. And I decided to go with the kilometers. So that's 61.3 kilometers.